Hello students, welcome to the fourth part of our first module in CFF. So students, in the previous session we have studied about the acoustic velocity A equal to, what was acoustic velocity? Root of dou P by dou rho at constant entropy or isentropic process, for an isentropic process. So students, if dou rho means it is change in density. So if dou rho tends to 0 or its value is approximately equal to 0 means the change in density is almost 0, means the body is incompressible. So the body is incompressible means A will be, if denominator is 0 tends to 0, A tends to infinity, right? So acoustic velocity will be infinity. So the pressure pulse in a medium, in a flow field, will be felt anywhere in that field instantaneously. So that is the idea about acoustic velocity being infinity. So A tends to infinity means what will be the value of Mach number? Since Mach number is velocity by acoustic velocity, if A tends to infinity, Mach tends to 0, very small value, right? Very small value. For incompressible flow, Mach tends to 0 or very less than very small value. Okay, so depending upon the magnitude of flow Mach number, depending on flow Mach number, the steady compressible flow can be divided into three types. The compressible flow can be divided into three types. First one, incompressible. Second, subsonic. Third, supersonic flow. So mainly three types of flow: subsonic, supersonic, and incompressible flow. So you know that for incompressible Mach number will be very small, tends to almost 0. Not exactly 0. I will tell you the value. If flow Mach number is very small, the effect of compressibility can be neglected and the flow can be assumed as incompressible. Okay. So practically this situation can occur in two cases, incompressible. First being the case with a very small velocity of flow. So incompressible in two cases. First, A, velocity almost 0. So practically this situation can occur in two cases. Which all are they? The first one is the very small velocity of flow, for which compared to the velocity of sound A, compared to velocity of sound or acoustic velocity A, V will be very small, almost approximately equal to 0. So the local velocity of flow is negligibly small. In that case, Mach will be almost be 0. So it means incompressible. Second case, large velocity, A infinity, Mach 0. Here also the flow will be incompressible. So whenever the velocity of fluid flow is almost 0, the flow will be considered as incompressible flow. Whenever the acoustic velocity is infinity in that particular medium, the flow of that medium is considered as incompressible. Okay. So that is in the case of incompressible. So if the flow Mach number is less than 1, then the flow is generally said to be subsonic. So if Mach number is less than 1, flow is considered as subsonic flow. So m less than 1 means v less than a. Velocity of flow field is less than the acoustic velocity in that medium. So such case it is considered subsonic. So sonic means sound of the speed of sound. Sonic is the word sonic is related to sound. Okay. So subsonic means the speed of the speed of the field or the velocity of the field is less than the sonic speed. That is v less than a. So that is why the word called subsonic. So if m greater than 1, m greater than 1 means v greater than a. So that is supersonic flow. Okay. Uh, Here the velocity of field will be greater than the sonic speed. So Mach number will be greater than. So it is known as supersonic flow. Okay. So I will give a very a precise range. Okay. So incompressible is considered. Flow is considered incompressible when Mach number less than 0.3. Okay. So any subsonic flow is less. Actually, it is considered as a Mach number less than 1, but clear range, a more specific range is 0.3 to 0.8 is considered as subsonic. Okay. So supersonic flow will be some 1.2 to m ranging between 1.2 and 5. Okay, in between that a transonic flow is there. Transonic flow. Okay, transonic flow it is 0.8 and 0.12. So it is somewhat subsonic and somewhat supersonic. So that range is between 0.8 and 1.2. Some sort of tolerance is provided from the value 1. So 0.8 is close to 1. 1.2 is also close to the value 1. So it is almost subsonic, maybe subsonic or supersonic. So that particular range is called sonic. Okay. When m is one more hypersonic is there. Okay. Hypersonic flow is when m greater than 5. Okay. So m equal to 1 means v equal to a. So such flow is sonic flow. Flow velocity same as that of sonic speed, sonic velocity, okay, or sound velocity. So that is a clear case of sonic flow. So just understand these ranges and all, yeah? And the flow can be classified into different types based on flow Mach number, local flow Mach number. So this is how classification is done. Now we will move on to the concept called flow regimes. Flow regimes means incompressible regime, subsonic regime, sonic and supersonic flow regimes. So students, I am showing the difference between the disturbance created, a point disturbance, the pressure field created by a point disturbance, then different pressure field created by a point disturbance in three different regimes. That is, first one, incompressible, not three, maybe four. Incompressible, subsonic, sonic, and supersonic regimes. So what will be the difference between the pressure field created by a point disturbance when the fluid we are considering, the flow we are considering is incompressible fluid flow or subsonic fluid flow, sonic and supersonic fluid flow regimes. So how this pressure field created is different in each of the four different cases. So that is what we are studying. So the disturbance may be created when an object moves in a relatively stationary compressible fluid, or when a compressible fluid flows past a stationary object. Okay. So in both cases, pressure pulses or the pressure wave are generated from the object, which are transmitted how radially outward in all direction with the velocity to the velocity of sound in that fluid medium, right? So I have a I have a fluid medium here. Okay, maybe this is stationary. First, stationary means the velocity is almost zero, so it will be an incompressible flow. Since the velocity of the medium is zero, or almost zero, it can be considered as incompressible regime. So I am creating a disturbance at a particular point here. So what will happen due to this disturbance? Some pressure field will be created such that it this pressure field will move radially outward in all direction. Okay. So with the velocity of what? Velocity of the sound. Velocity of the sound, right? So after 1 second, it will if a equal to oh, 1 meter per second. Okay, maybe in 1 second it moves a in 1 second in 1 second the sound moves some distance of a, so the sound velocity, the value will be a, the value of sound will be a. So after 1 second it will move, the pressure wave move with the velocity of a, means in 1 second it will, the radial distance will be a. After 2 seconds it will become, the pressure field will reach some 2a distance. After 3 seconds it will reach 3a distance, right? So students, when you throw a stone on a stone in a water source or in any ponds, or you can see that when you throw that, when the thrown stone reaches that water level, some ripples are created. What are those ripples? Those ripples are nothing but the pressure field or the pressure pulse that is generated due to the disturbance you have created by throwing that stone. So the pressure pulse generated is nothing but the speed of the pressure pulse generated is nothing but the speed of the sound only, because it moves radially outwards, right? The ripple is created in a circular manner, and this ripple gets enlarged by passing of time, and it will, the radius of the ripple increases with time, and ripples are again created if the disturbance continues. Okay. So that is the same idea here. The ripples are nothing but pressure pulses. Okay, the velocity of the ripples will be the velocity of sound only. Okay, velocity of sound only. So that is what happening in case of incompressible. Why this is considered as incompressible fluid flow? Because the velocity of field is zero. V equal to zero. V equal to zero. Okay. So this will be concentric circles. Okay. Some uh, so students, before that I will introduce some terms. Okay, some terms called A0, I will be drawing some figures. I will mark some terms here, so I will explain what those terms will be. A0, A1, A2, A3, etc. So these are positions of a tiny an object. I'm throwing some object in a fluid field, okay? Maybe a compressible, maybe incompressible, maybe supersonic, sonic, or supersonic. I'm throwing some tiny objects to create some pressure pulses there. So if the thrown or if the object thrown, maybe sometimes it may be moving with sonic velocity, sometimes supersonic, sometimes subsonic, or in case of incompressible, it will be stationary, same, because it doesn't move. So if this is our field, if this velocity equals 0, stationary fluid, if I'm throwing some stone here, so here some pressure pulse will be created, okay? If this field is if field is stationary, this object won't move. But if this field is moving with a velocity some 5 meter per second, naturally it will move, okay? So what is A0? A0 is the A0 is the current position of the object if it is moving. A1 is the position of the tiny object I have thrown 1 second ago. 1 second ago. A2 is 2 second ago. Position of the 2 seconds ago. The position of the tiny object 2 second ago. A3 is the position of the tiny object 3 second ago. So if A4 is used, means it is 4 second ago. Okay, so that's the concept. So make sure that you have understood what is meant by A0, A1, A2, A3, etc. Okay. So another term I am using is small a1, small a2, small a3. Okay. So for each of the previous locations of the tiny object, okay, for each of the previous locations of the tiny object, the present position of the wavefront generated or the pressure pulse generated at that time are drawn and marked as A1, A2, A3 respectively. So I will make you clear that. For example, if A1 represents the small a1 represents the present position of the wavefront emitted 1 second earlier. So you know that A0 is the present position of the object. A1 is the previous position of the object 1 second ago. 1 second ago. So small a1 is nothing but the wavefront generated, the present position of the wavefront generated, which was created during the or when the object was at a1 position. Okay, suppose the object is now at a0 position, but 1 second ago the object is moving or flow is in this direction. 1 second ago it was in a1 position. So uh, while the object was at a1 position, it might have generated what it might have generated some waves, right? Some pressure pulse. So the position or the position of the wavefront as of now, the position of the wavefront as of now, or the position of the wavefront emitted 1 second earlier, or the position of the wavefront emitted when the body was at a1, so that will be small a1. So what will be it small a2? Small a2 is nothing but, this is a1. Small a2 is nothing but position of the wavefront which was emitted 2 seconds earlier, or when the object was at a2 position. So naturally it might have become even bigger than a1, because some 2 seconds are passed now. So naturally the ripples will become even bigger. So at a3, this is a2, it might have become even bigger. Okay, so that is the idea of capital A0, A1, A2, and small a1, small a2, small a3. So students, I will make even more clear. So I am considering an incompressible flow. Incompressible flow means the flow velocity is almost zero, or the velocity the flow is almost stagnant. So in stagnant flow field, whenever you throw a stone, some concentric circles are formed. You cannot. So if you take some utensil and you fill it with water and you throw some small tiny particles in that water, ripples will be formed, which will be concentric only. Okay, but the tiny object won't move. Only waves move. Why tiny object don't move? Because the field is stationary. There is no flow of the water in that utensil, so the object won't move, but the waves move concentrically. So how that happens? So so a0, a1, a2, all the position will be same itself. Why? Because the object is not moving. Since the flow is incompressible, object is not moving, so all these four, or maybe up to a3 or a4, anything will be at the same point only, right? uh, so what is small a1? Small a1 is the wavefront generated when emitted when the tiny object was at the position of capital A1. Okay, capital A1. So how can we uh, draw that figure? With a1 as center, I will draw a small circle, and the radius will be small a. Small a is the distance traveled by sound in 1 second. In 1 second, or the velocity, the acoustic velocity, if the acoustic velocity a, acoustic velocity is taken as a, means in 1 second it will travel a distance of a, right? So after 2 seconds, what will be the distance travel? 2a. After 3 seconds, 3a, right? Now, so this what will be this circle? This circle will be a1 circle. The circle is named as a1. So students, now we have to draw a2. What is a2? A2 is the circle or the wavefront emitted 2 seconds earlier. 2 seconds earlier means when the tiny object was at position a2. So a2 is same as a0 or a1. So therefore I am taking the center as same for drawing the circle, but radius will be 2a. Why? Because it is the wavefront generated 2 seconds earlier. So I will draw a circle, a concentric circle with 2a, with 2a as uh, with 2a as the radius. Similarly, so this will be a2. The circle is named as a2. Similarly, you can draw a3 with 3a, with 3a as a radius, and this will be a3. The center will be same. So in case of incompressible flow, In case of incompressible flow, the pressure field will be some concentric circles only, concentric circles A1, A2, A3. You should note that concentric circles. The pressure field created will be concentric circles. Okay. Now we will move to So what are these circles? These circles are the sound waves or pressure pulse. Sound waves or pressure pulse or pressure wavefront or pressure disturbance. All these things are same. Pressure pulse or wavefront. Everything is same. Okay. So these are the circles. So we are studying the pressure pulses or pressure field created by a point disturbance in different types of flow. So this case is incompressible flow. Now we will move to subsonic flow. Okay. In case of subsonic flow, this capital A0, A1, A2 won't coincide because the fluid is moving with a velocity less than acoustic velocity. It means a subsonic velocity. Okay. So if the current position is A0, current position is A0. The position of the tiny object 1 second ago will be A1, right? A1. So the flow is in this direction. So this is the previous position. This is the position A2 2 seconds earlier. This is the position A3 3 seconds earlier. So students, in 1 second it will move from A3 to A2. In the next second it will move from A2 to A3. 1 second, 2 seconds it reach here, 3 seconds reach here. So this is the current position. Okay. So this is the current position. So the distance travel in 1 second will be equal because V is the velocity. But you should take care that since this is subsonic, it should be less than A. So whenever I am drawing a circle with the velocity A, it should be greater than the distance. Okay. I will show you. Now we have to mark this A1 circle, A2 circles and all. So what is A1 circle? What is A1 circle? Small A1 circle is the wavefront generated 1 second earlier. So 1 second earlier means, so current position is A0. So 1 second earlier the center was here. So you should draw a circle with the radius A. So radius A means it should be like this. It should be like this because this is A. So A should be more than this value. Why? Because B less than A. So this value is the distance traveled in 1 second by the flow. So the flow is traveling with a velocity V in 1 second, but sound is traveling with a velocity A in 1 second. Since V less than A, so the circle produced by wavefront should overcome this distance. So it must be bigger than this distance and this distance, right? So this also V only, but this radius should be A should be greater than V. So if this is A0, A1, A2, I will draw a smaller one, A1, A2, A3. 1 second earlier I am drawing a circle. So this is this should be a perfect circle. Okay. So it's with the center A and distance A. Okay. Now this circle is A1. Now you should draw A2. A2 is a circle with the center capital A2 and radius 2A. So it is 2A means to draw a circle like this. Center this one and radius 2A. Now A3 is circle with the center A3 and radius 3A. So I will draw it a little bit small. Okay, wait. A1, A2, A3. So students, this will be the type of pressure field created. So you have to understand that this is the current position of A0. I will mark with the red. Okay. So this is the current position of the tiny object. This was the position 1 second ago. So this A1 is the position of the wavefront, the current position of wavefront created 1 second ago. A2 was the position of tiny object 2 seconds ago. So this A2 is the present position of the wavefront generated when the object was at A2. This is the position of the tiny object 3 seconds ago. So this A3 is the position of the wavefront created 3 seconds ago, or when the object was at the position A3. So students, you have to note that this distance should be less than this distance. Okay, because since the flow is subsonic, the velocity of flow field should be more than the velocity of the tiny object or the flow field. So the wavefront should travel faster than the movement of when the tiny object reach A1 to A0, the wavefront should travel faster than that object. So that is subsonic flow. Okay. So you have to note that in the previous case it was concentric circles, but here it is some unsymmetrical. Right, you can see the pressure disturbance felt in all direction, but at all points in space. But the pressure pattern is not symmetrical, not symmetrical. Because here the A3 is having is a circle with the center A3 and radius 3A. Here it is circle with the radius 2A and center A2. This is circle with the center A1 and radius A. So towards towards it will have a larger gap, but here it is closely packed. Here closely packed. Here more space. So it is not concentric but an unsymmetrical wavefront. So this is the distribution of pressure pulse in case of subsonic flow. So a practical example to this is in case of an automobile moving with a subsonic speed. Means if a car is moving with a speed less than the speed of sound in air, the noise created by the engine of the automobile as well as sound of horn is heard before what vehicle reaches a person. Okay, so a vehicle is moving towards front. Okay, so a man at the front side of vehicle, a man is standing when the vehicle is moving and some engine sound is there, but the man will feel the engine sound even before the vehicle reaches the man. So that's the idea of subsonic flow, because the engine sound is traveling with the sonic velocity, or acoustic velocity A, but the velocity of velocity of the engine or the velocity of the car is subsonic only, lesser than the sound of lesser than the speed of sound. So that is the idea of subsonic flow. So you have to note down that this is an unsymmetrical concentric, not concentric, unsymmetrical circular pressure waves. So here, so now the position of AC, the current position of the, if this is an example of car I have told, so the current position of the car is only here. The car is moving this direction, but the sound has reached here. Understood? The sound has reached here. Even before car, sound has reached the front side. So that is the idea. Okay. Now I will move to the sonic flow. In case of sonic flow, this is A0 current position. This is A1 position of the sound object before 1 second. A2 position of object before 2 seconds. Okay. So you have to draw this circle with the radius a small a1. You have to draw small a1. Small a1 is nothing but pressure wave. The current position of pressure wave emitted 1 second earlier. 1 second earlier means when the object was at a1 with the velocity of, so I am considering sonic v equal to a. V equal to a. Velocity of object and sound velocity should be same. Okay. So at a1 with the, so this distance is v and this distance should be equal to a. Okay, so the circle I am drawing should be like this only. So this should also be a. So this is a. This circle is a1. Similarly, if I have some a3 position, okay, here a2 I have drawn. Small circle A2 should be drawn with the center capital A2 and radius 2a. So this distance is 2a, right? So the circle A2 should be like this. So this should coincide. Okay. So this is A2. So this radius should be 2a. So I will draw it. It should be like this only. Okay. So current position is A0 here. So this is A1. So this should be A2. This should be A3. Okay, this is small a1, small a2, small a3. So this should be a. This should be 2a. This should be 3a. So all the wavefronts should coincide at or coalesce at that current position of the object. Understand? So all the disturbance created by the body should intersect at the point A0. At A0, it should intersect on the body, and they all are contained in the half plane of the right of the body. So if I am drawing a plane in this through this A0, all the sound disturbance are to the right of the body only. So here this is known as zone of action. Zone of action, and to the left of the body no wavefront is there. To left of the current position of the body no wavefront is there. So this is zone of silence. Zone of silence. So that is very important, since here the wavefront, so the current position of the body is at A0. The wavefront never overtakes this A0. So the wavefront is intersected or culminated or coalesced only at A0 only. So here wavefront is distributed, but to the left of this A0 there is no wavefront. So the wavefront never overtakes. Wavefront never overtakes the body. Overtakes the body. Right? So that is why here a zone of silence. Zone of silence means no sound. Here zone of action, there is sound. Okay, so whenever a car travels with a sonic velocity, even if a car is having engine sound, but it won't reach a man who is standing in front of that car until the car reaches the man. Okay, the sound and the car reaches the man at the same time only, because the sound of the car cannot overtake the speed of the car. Okay, the sound velocity can never overtake the speed of the car. So that is the idea of sonic regime. So here all wavefront concentrate at zero, a0. Now I will move to the supersonic. So in supersonic v should be greater than a. So here a0, a1, a2, a3. I've drawn all these things. Okay, so this is v, but a should be less than v. So if I'm drawing a circle with a small a1 circle, I'm drawing a1, so it should be having center a1 and radius a. So this will be like this only. It should not overcome a0, because it should have a radius a, and a should be less than v only. Okay, so similarly I'm drawing a2. So a2 should have a velocity, so a2 should be like this. Okay, a3, this is with 2a, a2, and a3 will be with a3 as center and 3a as. So this will be like this. So students, if you can draw a line tangential to all these circles starting from a0. So this will form a cone. So students, the object is moving rightwards. The current position of the object is a0, but nowhere all the sound waves are trailing back. Is at the back. Is positioned at the back of the a0 only. So it can never reach a0. So a0 is always ahead of the sound waves produced. Okay, you can see a0 is always ahead of the sound waves produced. So this thing is known as mech cone. Okay, if I am drawing this a line through here, in this angle is mech angle alpha mech angle. Okay, so how can you calculate mech angle? So this is a3, the distance between a0 and a3 is how much? velocity distance traveled by object in t seconds. So it is vt. Okay, vt, and this will be at. Okay, I will draw it once more. So you just try to understand that this in case of supersonic field, a Mach cone will be generated by the waveforms. Mach cone, a conic shape, because the velocity of sound is always less than velocity of the flow. In naturally, a conic shape of wavefront is produced. That cone enclosed by the common tangent is called as Mach cone. Okay. Students, I have drawn it once more. So this circle is A1, this circle is A2, this circle is A3. So this angle is alpha. So this cone is Mach cone. Okay. This alpha is Mach angle. So all this space is zone of silence. So here no waves, sound waves are there. The zone enclosed by Mach cone is zone of action. Zone of action is the space enclosed by this Mach cone. Okay, how to, if this is position A3, okay, this is A2, A2 will be somewhere here, A2, A1, A0, this is the present position. Okay, so students, what will be this distance? So this distance will be the radius of this circle. This will be 3a, or this is 3 seconds earlier. Okay, here 3a. What will be this distance? This will be 3v, 3a and 3v. So this angle is nothing but this will, since this is tangent, this will be 90 degree. So you can get a Mach angle sine alpha as opposite side by hypotenuse. Hypotenuse is 3v, or a by v, or 1 by Mach. So alpha is equal to sine inverse of 1 by Mach number. So Mach angle is nothing but sine inverse of 1 by m. The Mach angle is defined only for supersonic flow. Only for supersonic, okay? So Mach angle is not valid. There is no Mach angle for incompressible or subsonic or sonic flow. It is valid only for supersonic flow. For when m equal to, if m is 1 means sonic. Sine inverse of 1 is 90. Sine inverse of 1 is so Mach angle is 90 degree when in case of what, in case sonic velocity, and for when in case of subsonic it will be infinity. So when m equal to 1 sonic, right? So alpha equal to sine inverse of 1 by 1 equal to 90. So in case of sonic, Mach angle will be 90. When m equal to infinity, Mach equal to infinity means alpha equal to sine inverse of 0 is 0. So these are the different values, okay? Don't worry about that. Mach angle is defined only for supersonic flow. So what is Mach cone? I will define Mach cone. Is the wavefront that enveloping in a conical region. All the disturbance in case of supersonic flow, all the disturbance wavefronts enveloped in a conical region, as you have seen, called mech cone, or it is also known as Mach wave. Mach wave. This Mach wave separates zone of silence from zone of action. Okay. The conical surface separating the zone of action and zone of silence forms a wavefront termed as Mach wave. So with this, I will stop this session.